Thank you. Sorry for the delay. So what I'm trying to present today is a kind of journey and a series of toy model. I'm not pretending that I have any model for really describing the emergence of space-time. I will have analogies and models, but I will try to convince you that you can learn already something about what should happen if gravity is indeed emergent. And even before I take that, I would like to start with an issue, which is why gravity should be emergent. Because at the end of the day, I think it's always important for us to have a better motivation for what we try to do. So gravity is a theory, really general relativity is a theory that works in all possible respects in nowadays, right? We have tested at several different scales. We use it every day. When you find your way here, you're using the GPS. The GPS is using a correction both from special relativity and general relativity. And general relativistic one, the time dilation by gravity is the most important. It needs to be corrected, the GPS, otherwise you will never get here, right? So we really use general relativity in everyday life. Nonetheless, general relativity is a particularly strange theory. It's a theory, first of all, that predicts its own demise. It's a theory where we have singularity theorems that are basically telling you that working within a theory, you can predict an end of predictability of the theory. It also predicts very strange things. It predicts that objects which are purely gravitational behaves in a thermodynamic way. It has a critical phenomena in gravitational collapse. General relativity explains our universe, if you like, a pie that nobody ordered, because basically you have to account for an immense amount of dark energy and dark matter. It has strange duality as holographic behavior. It has wormholes, faster than light solution, possibility of time travel. It has very weird things. So it cannot be the definitive theory of nature. And most of all, has this intrinsic thermodynamic behavior. When you see thermodynamics in physics, you immediately think that there is a substratum, that there is something that you are constraining above, right? So I will now want to focus as a motivation, first of all, on the so-called space-time thermodynamics approach, taking a step back. My step back is a step that brings us back to 1973. So we are back in 1973 at the end of basically almost at the coronation of the so-called period of the Renaissance of general relativity. 1973, there is an historic paper by Bill Carter-Hawking that is putting together the wealth of knowledge accumulated over the last years and basically presents 4 laws of black hole mechanics, which seems to be in strict analogy with the 4 laws of black hole thermodynamics. But of course, these 4 laws at the time were resting on a very weak assumption that black holes were thermodynamical objects, but classical black hole cannot emit anything. So you can even demonstrate that if you have black hole that cannot radiate, but you work with them like thermodynamical object, you can build easily violation of the generalized second law, that the total entropy of the universe would be decreased. So this system of laws became consistent in 1975 with Hawking when it was discovered Hawking radiation. So black hole indeed can radiate. But how they can radiate? They can radiate when you do a next step, which is putting quantum fields on a black hole spacetime. Nothing to do, by the way, with general relativity. It's quantum field theory on a fixed background, right? Now, think about it for a moment. How the heck general relativity knows about quantum field theory and curved spacetime? Why general relativity has theorems that are predicting, almost begging, for black hole to radiate? That's weird. That's absolutely weird. And if you ask to the people that were at the center of that revolution, they were also somehow surprised by this. But this is something that is screaming from the fact that there is a deep connection between quantum matter and gravity. Of course, if you have an emergent framework where all these degrees of freedom, where gravity and matter are emerging from a substratum which is common, this is much less puzzling. But now, if this idea works, there should be a way to reverse the idea. That means, okay, but then it should be possible by quantum matter on a non-dynamical spacetime to arrive to the Einstein field equation. Because these theorems of GR that are the laws of black hole mechanics are coming from the Einstein field equation. So how you can reverse engineer the argument? You take a field and you put it on Minkowski spacetime, the simplest spacetime you can. Now, Minkowski spacetime has a symmetry group, which is a boost invariance, right? It's part of the Lorentz group. When you take an orbit of the Buskilin vector, which is also the orbit of an uniformly accelerated observer, this observer sees an horizon. And and you can basically split the Minkowski spacetime in two wedges, the right and the left Rindler wedges. They are characterized by causal horizon, which in this case are observer dependent. But still, they are underlying a general theorem, which is that the vacuum in Minkowski space can be seen basically as a product of vacuum on the two wedges. There is a theorem, the so-called Bisoniano-Wickman theorem, that proves that in a rigorous way. Now, what is telling you? It's telling you this, that when you see Minkowski space in this way, your vacuum becomes, on one side, thermal, at a temperature, which is the Uru temperature, which is proportional to the proper acceleration of your observer. And at the same time, given that you can always define a reduced density metric tracing on the wedge you cannot access, you have a mixed density matrix that for which you can compute an entropy of von Neumann. And this entropy comes to be proportional to the area. Exactly like the Becker-Steinhoff. So the two ingredients, what they are, that starting from Minkowski, you have a setting in which you can recover a temperature akin to the Hawking temperature and an entropy akin to the Becker-Steinhoff temperature. Yes?
This horizon area is infinite, right?
Yes. It's an entropy density. That means that there is an entropy per unit area. In any case, you can always, in a certain sense, cut off this area. In fact, actually, you need to put in any case UV cutoff as well, no? Because otherwise the correlation across the horizon will give you a UV divergence. But you can always think of it of entropy per unit area, okay? And entropy densities. That is what is really crucial. Here I was simplifying a little bit the story to not get too much into the details. This is the starting point for the coming back. So coming back, what you use? You use the equivalence principle. Which principle? We want to recover GR. The only theory in 4 dimensions that describe gravity, spin to particles, which satisfy the strong equivalence principle, is general relativity. The strong equivalence principle is the weak equivalence principle extended also to self-gravitating body. Is local Lorentz invariance and local position invariance, both of gravitational and non-gravitational experiments. Okay. Now, what you do? You do the following exercise. You say, okay, I pick up a point in any spacetime. I take a neighborhood of this point. The equivalence principle tells me that if it's sufficiently small, it will be a portion of class spacetime. There I can construct a local Rindler wedge, and I can do this following exercise. Imagine I perturb my horizon by a flux of matter crossing it. And this horizon wants to go back to equilibrium in the future, where the equilibrium point for me is the point P. I look at the weight relax, and I impose that the entropy, the variation in entropy, the variation in energy of the horizon are related by a Clausius equation. I'm basically imposing a thermodynamical equation to start with. The variation of the entropy, I just told you that is basically proportional to the variation of the area. The variation of the area is related directly to the variation of the expansion of the congruence of null geodesics, which is drawing your horizon. And this variation is described, theta dot, if you like, by the so-called Reichenau equation, which is a pre-geometric equation, doesn't know anything about the equation of motion of your gravitational theory. It just describes how theta varies along the affine parameter, and is a function basically of theta squared, sigma, the shear square, and the Ricci tensor in that region of space-time contracted twice with a null vector along the horizon. Regarding the heat, what you do is that you assume that what perturbs the horizon is a flux of matter, so you introduce a stress energy tensor, and then you impose the Clausius relation, and you impose that your stress energy tensor is covariantly conserved. These are the ingredients. If you do this, you get to this equation. This equation is basically, you see, this is the Einstein tensor. This is an integration constant playing the role of the cosmological constant. And this one is the matter content. Alpha, as we say, is the related basically to the proportionality with respect to the area. It's the area density, if you like. The area density, if you fix it to be 1 over 4 pi for h bar g Newton, is exactly giving you the Beck-Steinoff intent entropy, but it's not so much the point. The point is that it's giving you back basically the Planck scale, and basically giving you back the Einstein field equation with the proper constants. Now, in this derivation, I just cheated because so one point, we can go back. So this is a strong hint that the assumption I did at the start is right, okay? Secondly, here, in order to arrive to this, I throw the shear because I assume that the shear here goes to 0 rapidly. This was an assumption that Jacobson later on recognized to be false. It doesn't go rapidly back to 0. And what you have really to do is to not throw the shear. But then, in principle, is an abstraction because that shear term is not in the Einstein field equation. But what you can do, you can interpret the Clausius, you have to generalize the Clausius equation to near equilibrium thermodynamic. In near equilibrium thermodynamic, you have a reversible part and an irreversible part. The reversible part is related to the fact that when you do a thermodynamical transformation, I'm not just producing waves through the table. I'm heating up the table. I'm exciting internal degrees of freedom, right? So this is the internal entropy production, which is related to the so-called unmatched heat. It's the part that you cannot describe on the it's part of the excitation of the substratum. If you look what is, in this case, the unmatched heat, is exactly a term well known in general relativity, which is the so-called Hartley-Hawking tidal heat. And what is the Hartley-Hawking tidal heat? It's the energy that you release at infinity when you shear the horizon because you perturb it. The horizon wants to destroy to go back to equilibrium and emits gravitational waves. And this is basically what gives you the Bondi mass that you measure at infinity. So it is exactly showing you that the gravitational waves, that by the way, you cannot put in Jacobson construction because they don't have a covariantly conserved stress energy tensor. They have a pseudo stress energy tensor, right? It's partially with the partial derivatives. And they enter in Jacobson construction as a matched heat. So the gravitational waves in this picture are not waves on the spacetime. They're in the spacetime. They are equivalent of heating up the table. The picture for which we look at the deformation of spacetime is just a simplification, very useful, but maybe it's not the full picture. The fact that you stretch spacetime, it's just that you complexify the spacetime in its interior. So this is how it seems to suggest. And let me finish this. If you look at what is the viscosity, the coefficient, you call this the viscosity coefficient, you get that the viscosity coefficient on the entropy density satisfy exactly, gives you 1 over 4 pi, which is the so-called KSS bound for people that is more in string theory and IDS-CFT. Yes?
Why you're saying that this dissipative term corresponds to heating up the table because aren't the gravitational waves carrying energy away?
And that is exactly. The problem is that they carry energy, but you cannot localize them. They are not defined by its covariantly conserved stress energy tensor. There has been, you are too young, but there has been many years ago, people that was claiming that due to this, gravitational waves do not carry energy. I saw a very big heated debate between Charlie Misner and another guy I will not nominate, that was saying that they were not going to see any gravitational wave because they cannot carry energy due to this fact. So instead, here, they carry energy. It's not that if I put a thermometer here and I keep eating, this thermometer change its status. They carry energy, but the energy is carried through excitation of the internal degrees of freedom, they're not equivalent to the phonons of the table. You see what I mean? Okay, so this is, okay, if you can eat it, there is a way of saying, but this is a paraphrasis of Boltzmann. If you can eat it, it has microstructure. That's the idea. Okay. Now, this is why many people and many scenarios nowadays, in a certain sense, when you have to get from a discrete and quantum reality to a continuous and classical spacetime, it's very natural to resort to a concept of emergence because it's something we are familiar with, maybe not so much in theoretical physics, but in the rest of physics, yes, in the rest of physics. Okay, so now I will try to do, in an humble way, an approach which is not trying to tackle the full problem, but just try to understand how it may work by adopting toy models and starting from terra cognita. And terra cognita is condensed matter physics. So let me point now to condensed matter analogs. What are condensed matter analogs? Condensed matter analogs are systems where you can look at the perturbation on a background and show that they propagate like fields, in some cases even quantum fields, on a curved background. So you can basically reproduce everything of quantum field theory in curved spacetime. Okay? Cosmological particle production, black hole evaporation, all of this can be reproduced. Normally, the way this perturbation react on the background is not described by the Einstein equation. Of course, otherwise I would be not here, but at the academy. Okay, so the point is that they are described by field equations which are not the Einstein field equation. But still that they can carry on a lot of information, as we'll try to convince you. So let's move on. So the topical example is acoustic gravity. What is the basic idea? You have a continuity and order equation for a fluid. You take it to be a perfect fluid and irrotational. What I mean by irrotational, it means that the velocity of the fluid can be written as the gradient of a scalar. This scalar is the so-called velocity potential. Okay? So a very simple system. You take this system, so you perturb in all the physical quantity, the density, the pressure, and the velocity potential, and you can have a set one of these three. Two can be compressed because you have a barotropic equation state, so you can eliminate one of the variable. And for the other two, basically from two linearized field equation, you put them together, you eliminate the variable, you get a second order field equation. Normally what you get is the second order field equation for the velocity potential, which looks very odd, but if you introduce this metric, you can write this as the Laplace, the D'Alembert on a curved spacetime, where this is the acoustic geometry. So acoustic perturbation on a perfect fluid, which is envisaged and irrotational, propagate like the velocity potential perturbation propagate as a scalar field, a massless scalar field on a curved background. These are not all the possible metric of GR, but a good chunk of it, mostly the most interesting one, like black hole metric, cosmology, you can do it with this one. Okay, how you do black holes? Well, first of all, you have a dictionary. You can convert basically where the region where you have a supersonic flow will be the region internal to a black hole, is a trapped region from the point of view of the sound waves. And you can build acoustic black hole in many ways, like Laval nozzle. You can have double Laval nozzle if you can even do a wet hole horizon. In concrete experiment with Bose-Einstein condense, for example, they do a waterfall in such a way that here you achieve a sonic point, or you can manipulate the speed of sound with the so-called flashback resonance. So the flow is always at the same speed, but you change the speed of sound, you create the horizon the other way. Yeah. We will go back to this. Now the problem is that can gravity, not just the metric, emerge analog? Can we do that? Now, there are two theorems that seems an abstraction for emergent gravity. One is the Weidner-Witten theorem. The other one is the Marov theorem. The Weidner-Witten theorem basically tells you that spin-2 particle cannot be composite. And if you start with Lorentz invariance, engage invariant current, and conserve stress energy tensor. So Of course, in this case of the annual gravity, we will see that given that you have a substratum, Lorentz invariance is not an exact symmetry. We have got a relativistic field equation, but that you will see in a realistic system is true only for long wavelength form excitations. Marov theorem is a bit more subtle because it's basically telling you that if you want to have an emergence of analog, basically what you need, if you want to recover a background-independent structure, exactly background-independent structure, you have all that there is a different notion of locality between the substratum and the emergent system, but that should really change in an abrupt way, because what he has in mind is like a second-order phase transition. You have the substratum, something happens, and everything emerges like we see it here. It's not that there is no mesoscopic physics, okay? And both the theorem, in a certain sense, are you have to get around if you have a mesoscopic regime, because if Lorentz invariance and diffeomorphism invariance are accidental symmetry. What I mean by accidental symmetry? They are symmetry that are never realized in an exact way. They are more and more accurate the lowest you go with respect to some very high UV scale. I mean, in this sense, we will live in cold atom physics, you see, with the analog of cold atom physics of quantum gravity. Then, in a certain sense, you can get around both the theorem, but it's important to have them in mind. This is why I expect that this mesoscopic regime must exist if the idea works. But this is good, because it's the mesoscopic regime that allows you for doing quantum gravity phenomenology. Otherwise, without mesoscopic regime, there will be no way to see deviation from the standard, from general relativity to special relativity. Okay, let's move on. So now I try a very simple toy model. And in this toy model, I want to try to do an exercise. Imagine that whatever it happens that from the substratum, which is quantum and discrete, I emerge a set of equations which are very simple. I have a bunch of fields, and I'm also assuming that basically the Lagrangian for the n fields factorize in a product of a Lagrangian for each field. But you see, the kinetic term, I'm assuming that it's done in Euclidean flat spacetime, no time, purely Euclidean space. Can I get anything similar to our reality from this? It seems a very simple system. It's basically, for those of you that are bit in cosmology, it's a form of K-essence. Okay, let's move on. Do the field equation. And let's try now to expand around, we take the solution of this field equation and expand around this solution. So I have an expansion for the field and for the kinetic term. And then I see what I get. I get a bunch of terms, not so nice. But let me analyze the term. The first term is the Lagrangian for the background fields, okay? The second term basically is linear in the phi, no? In the perturbation, but this is a zero by the field equation. If you are on shell, it's zero. The second term is the interesting one. It can be split in the case in which k is different from L, no? Or where you have k equal to L. If the k is different from L, you can always adjust your theory in such a way that goes away. So we simplify the analysis, we fix f in such a way that this cancels. Then you're left with this one, and let me now rewrite this term in this way, introducing a metric, and this metric will have this structure. You see, for those of you that are familiar with this structure, this is what is called a disformal geometry. Normally here you have Minkowski. Here instead you have basically the flat space, Euclidean element. Okay, note that this geometry is non-trivial. It's not, you get that the perturbation, this is telling you that the perturbation at this order, if you truncate here, move on affected geometry, which is not the original Euclidean flat geometry, but is as a correction, and this is due to the fact that the kinetic term we are taking are no standard, are K-essence, are function of the kinetic term, are non-linear in the standard kinetic term. Okay, so in principle you have many different metrics for each because it depends on little f. But let me do that all the f are the same. At that point, all the solutions are the same. And I get a single metric for all the fields. And then I say, okay, I want now this metric, this formal geometry, to be Minkowski metric. And you can immediately see that you can impose apt condition using, in a certain sense, the symmetry of your system, the fact that there is a symmetry under rotation. You can reduce this to pick up any direction and write it just this in this affine form. And then you can find one particular form of the Lagrangian and some set of value of alpha for which the metric is Minkowski. So what we have seen, that I started from a purely Euclidean reality, just with the weird K-essence Lagrangian, and I produced that the perturbation, which would be asa, fill Minkowski metric. So time, the signature, has emerged, and is that, but it's not emerged dynamically. It's just that the perturbation, they always fill Minkowski. They don't know that the substratum is Euclidean. But can we stop only here? Well, you can do even more, and here comes really the surprise. Okay, you say, okay, now I look at the obtained for Lagrangian, and I can rewrite it in terms of a real multiplet, right? Very good. Now I notice that there is an emergent ON global symmetry. There is an invariance under rotation in field space, and I can make it evident by taking out, doing a field redefinition, change of representation of the theory. So I take a common amplitude out, and which does, well, this one works, which doesn't basically transform. Phi doesn't transform under ON, while this transform under ON, and it's basically it's done that the norm of this should be L squared. This is basically a way to make the ON symmetry evident. Why I do this? Because now I can take this equation and decompose it in an equation including phi, capital phi, an equation basically for capital phi, an equation for the little phi. And now look at the surprise, because I can rewrite this equation. If I introduce a conformal metric with the capital phi is the conformal factor, I can say that, okay, I work basically, if you like, with a generic metric, imposing that is Weil flat. For those of you that do not know what it means to be Weil flat, it means that the geometry has to be conformally flat. When if your geometry is phi squared times eta mu nu, your phi is flat. So I say I can forget about eta mu nu. I say I work and live on a curved geometry which has a constraint to be Weil flat. And now what happens? It happens that if I realize that the Ricci scalar of this metric can be written in this way, I get this equation. The Ricci scalar is equal, constant, the trace of the stress energy tensor. And then I have a Klein-Gordon equation for a massless scalar field on this spacetime. You know what it is? This is basically Renault from gravity, the only other theory of gravity satisfying the strong equivalence principle in fourth dimension, which was discarded only because it was produced by Nordstrom in 1913, trying to make relativistic the Poisson equation. And the equation that I just showed you is called the Einstein-Fokker equation. It is the progenitor of GR. It looks like the trace of GR, no? Modulo sine. So anyway, we got completely, from that system, we got very, very close. This is a theory of gravity with a nonlinear sigma model. Okay, so as a first tentative, is already amazing that we did it. And this theory, of course, everything is emergent. If I go to the next order, the third order, I have a term that spoils the background. Well, I will comment on the background. It spoils even that reduced diff invariance that there is in Nordstrom gravity, because Nordstrom gravity is not a diff invariant like Einstein gravity is, because the causal structure of Minkowski is fixed. All the metrics are conformally flat. It was discarded because you cannot bend light. When Eddington saw the bending of light, it's clear that you have to resort to GR, not to Nordstrom gravity. But, so it's not fully diff invariant, but it's as close as you can go. Okay, and this next term will basically break all the things. It will break Lorentz invariant and break differ. It is a next subleading order, but it shows you that these are symmetries which are emergent, exactly like we wanted. Now, can we play with something more close to reality, not an adopted model? And here I introduce Bose-Einstein condensate. Bose-Einstein condensate are basically a form of superfluid from this point of view. I will show you in a second that basically you get a particular kind of superfluid, envisaged in rotation. So what you do, you have a bunch of atoms, normally 10 to the 5, 10 to the 6, pulled down in an electromagnetic trap. They go all in the same, almost all in the same quantum state, the ground state. And what you can do is that the initial equation describing the quantum, the field describing the atoms is a nonlinear Schrödinger equation. This nonlinear Schrödinger equation is taking into account that the atoms interact and they have a potential, a chemical potential. And this interaction is ruled basically by the S-wave scattering length, this A. And now what you can do, you do a mean field approximation. You say, okay, this is a quantum object, but given that all the atoms are basically in the same quantum state, I take the expectation value of psi on an almost coherent state. I say almost, it's not exactly a coherent state because you are in an eigenstate of the number operator. That cannot be exactly a coherent state, but it is with a very good approximation, a coherent state, highly populated. So you take an object, a value so on a almost coherent state, highly populated, it becomes a classical object, as a number, and that is your superfluid that you play with. It's the background. It's the classical spacetime. Okay. Now you have the quantum excitation over it. And you can prove that, of course, the vacuum for the atoms is not the vacuum for the excitation. The excitation people talk about are the phonons. And what are the phonons? You do a Bogoliubov transformation in such a way that you don't diagonalize the Hamiltonian for the excitation. So you have the standard nice multiple of the harmonic oscillator Hamiltonian, and you get the phonons on the condensate. We see these phonons. They are a reality. Phonons are something that we measure. You cannot touch them, but you can see them, okay? I'm not talking about abstract concept here. This is stuff that is done every day in the lab. So now what you do, you insert this answer, the mean field plus excitation in the original equation. You have an equation for the background, an equation for the excitation, right? And you see the equation for the background has this anomalous density, anomalous mass. So these are the way the excitation back react on the equation for the background part. If you neglect this part, you have the so-called Gross-Pitarevsky equation, which is the equation describing how the classical part in your mean field approximation evolved. Is your pure vacuum geometric dynamics in this language. Why do you say is the vacuum geometric dynamics? Because I'm going to show you that the second equation, the one for the excitation, if you do a Bogoliubov transformation, which is the so-called quantum Madelung representation, but in reality is a Bogoliubov transformation, what you do, you have an equation that looks like a continuity equation, an equation looks like an Euler equation modulo this term that spoils it. You say this term is suppressed by h bar squared. Let's forget it for a moment. I throw it away. This is the quantum potential. If I throw it away, I can repackage the other things exactly like I did before. The perturbation in the velocity potential of the excitation, they follow an acoustic geometry that now is determined with a constant determined by the microphysics. If I don't neglect the velocity, the quantum potential, that is the quantum correction of what I get that my dispersion relation, that my particles do not satisfy a purely massless and Gordon and a curved spacetime. They have a correction. This correction breaks Lorentz invariant because it's purely spatial. And this correction is still very small because it's suppressed. What is h over 2m? It's basically the acoustic quantum wavelength. That is the scale that, and it's related to the scattering length, and is related to what is called the Hilly length of the condensate, which is the typical coherent length of the condensate. You have a modified dispersion relation, UV Lorentz breaking. This is your phenomenology that would be the signature of the emergence of space-time in the system. Now you can ask yourself, and this was the main motivation, is Hawking radiation robust? You can produce an analog black hole, a sink. If I can quantize phonon, like I can in Bose-Einstein condensate, I should see Hawking radiation. It's a purely kinematical effect. Hawking radiation doesn't use the Einstein equation. The answer is that you still see it. Basically, you predict a correlator's pattern in the phonons that you see in the lab And you also can reproduce that there is a regime when you have a spontaneous Hawking radiation as predicted, at the temperature predicted by the surface gravity of the black hole. This is another fact. Now we see it. It's no more speculation. The problem is why we see it. Now, I don't have time to explain it, but if you want, I will answer question later. But basically what is happening is this. If you have a superluminal dispersion relation like the one I just told, if you take an Hawking quanta and you trace it back toward the Killing horizon, instead of accumulating here, it will come from behind the horizon because it could be seen as something moving forward in time faster than light. The horizon is not anymore a barrier. Then you would expect no Hawking radiation because there is this feeling is what produces the exponential that what produces the thermal. But what is happening? Is happening that if you look at when you deviate from the purely exponential behavior, it happens in a region where your particles are still virtual. You see, gravity has to do a work to take two virtual particles, separate them enough, at least the quantum wavelength or the Broglie wavelength, so that they have to go on shell. But when they go shell, they are farther away from the horizon, and they are basically here, in this point where the real trajectory, red, and the relativistic trajectory, blue, are basically undistinguished. So whatever it happens here, dissipation, modified dispersion relation, whatever crap that appears, Hawking radiation is insensitive as long as the scale of Hawking radiation, the surface gravity, was inverse, is the mass, is very separated by what? By the scale of the new physics, the scale of Lorentz breaking. Okay? If you have this separation of scale, you're fine. And we understood it thanks to these models. Before it wasn't understood. This was the so-called Planckian problem. We also understand, I think, better also the information loss problem, but I have no time now to talk about it. If you want to, you will ask me. Now, given that we don't live in a Platonic world, but we have laboratories and we have astrophysics experiment, you can say, okay, so maybe we are emerging in this way, and Lorentz invariance is broken at UV. Can I look for these effects? The answer is yes. You can look and you can constrain this effect. Okay? And how you constrain this effect? You can, one way is, okay, let me take the standard model, and I add order by order, Lorentz breaking term, and I divide the term if they are CPT even or CPT odd. Because Lorentz breaking can come with terms which respect CPT. There is an inverse CPT theorem by Greenberg in 2003 that shows you that Lorentz invariance does imply CPT violation. You can have CPT violation implies Lorentz violation, but Lorentz invariance can be CPT even or odd. So you categorize basically order by order if you have operators which are CPT even or CPT odd. Normally people would prefer CPT even terms because there is a convention that CPT is more important in a certain sense than Lorentz invariance. How you constrain? You look at time of flight. If you have dispersion, particle of different energy will cover the same distance from a remote object in cosmology to us in a different time. If you have a good reason from the astrophysics model to say that they started at the same time, and you have a lot of statistics, many models, like many gamma ray bursts, then you can basically check if there are this delay that should increase with distance, right? Another things you can do is that if you have CPT odd terms, they predict a different propagation for different velocities. So what is happening is that if you see linearly polarized light, from example from the Crab Nebula, which is equal to 2 kiloparsec away, is a pulsar, then you can say, okay, if this light is polarized, but different helicity travel at different speed, you see that you have basically Faraday rotation even in vacuum that destroy linear polarization very rapidly, and you can cast a very efficient constraint. Or you can have threshold reaction. In QD, gamma that goes in a plus and minus is forbidden, right? Or an electron cannot Cherenkov in vacuum. But if you have a modified dispersion relation, you can see you can conserve energy, and so the basic vertical field are allowed beyond some threshold. So in this case, you can cast other constraints. If you see very energetic particles propagating, they should not propagate because if they interact with all the vacuum modes, they are dumped immediately and below pressure. And then the synchrotron radiation is very sensitive because as a typical critical frequency, that depends on a gamma factor, but a gamma factor with a dispersion can have a pole, can be bounded. You pump much energy in the electron, the gamma factor will not go beyond some limit. you will have a maximum and then decrease again. So you can cast constraint also this way. And we have now many constraints. Unfortunately, the strongest of them are based on cosmic ray physics, where we now have a lot of uncertainty about the nature of cosmic rays. Another possibility is that if you have a substratum, you have dissipation, because basically you exchange energy with the substratum and you have dissipative effect. Actually, there are some relation called the Kramer-Stroming relation that tells you if you have dispersion, you have also dissipation. There is a link between the two. And you can show that the lowest order dissipative term is the one that would be induced by a viscosity of spacetime in this case. Now you can cast a constraint to say, okay, the dissipation should be the typical decay, the energy loss rate should be such that is compatible with the fact that I see, I don't know, 80 TeV photons from the Crab Nebula arriving to me. You know the Crab Nebula is 2 kiloparsec, and you get that the dissipative coefficient should be less than 10 to the minus 26. So you see, and you can go to the next order, will be k to the 5, and here we have a constraint of order 1. Basically, we don't have a constraint. So if space-time is a fluid, it has to be a superfluid. Okay, let's move on. Another thing that we can constrain is maybe don't have, if I want to insert a scale in the Klein-Gordon equation without breaking Lorentz invariant or induced dissipation, maybe another thing is that I promote the box to an F box where the length scale will be here just for the dimensional region. In this case, of course, given that it's a function of the D'Alembert, it's still the Casimir of the Lorentz group, I don't break Lorentz invariant, but I introduce higher order derivatives, both in space and in time. I don't have a ghost because I introduce an infinite amount of them. In this sense, this is a form of non-locality. In this case, you can have, for example, in causal set theory, this is what, if you expand this F box, you have this kind of structure. If you have a string field theory, there were suggested this other kind of an analytical form. In both cases, you can constrain things, because in this case, you will have that the support of the propagator of a massless scalar field will be not just on the light cone, like the Strom-Huygens principle would tell you, but also slightly inside. And then, for example, detector that never have a causal connection, that they switch at different time, and there is not, they have only a time-like connection, and for a massless scalar field should not be influenced, can be influenced. Or in string field theory, you can see that basically the Wigner function, basically what is happening, you go in the relativistic limit, non-relativistic limit, you have Schrödinger operator plus Schrödinger square plus Schrödinger cube and so on. And then you can analyze, for example, the motion of a center of mass of a tiny oscillator in a lab. And it's an experiment that in principle can be done if you, in the future, if you have to pull down you have to kill all the possible environmental effects. Okay, so now let me go for another point. Okay, this is all nice, but in a concrete analog system, how close to Einstein equation we can get, and what we can learn from this exercise. So let me try to do it very rapidly. So you go back to the equation for the background with the back reaction term of the excitation. So this is basically the Gross-Pitaevsky plus the background effects, the back reaction effects. And now, you see this, if you want to be a geometrodynamical equation, it should be a non-relativistic gravity. So it should be something like the Poisson equation. But in order to see something, you cannot work with massless excitation. You need to have a massive excitation. And there is a simple trick to do this. You softly break the one symmetry by adding a term like this. And this is something that in the labs also is realized. And basically, you get that your phonons acquire a mass. Now they can gravitate a la Newtonian way. So the next step is to identify. You want to see if you can recover something like this. This is the best you can do in a non-relativistic substratum. Okay, you have to identify what is the analog of the gravitational potential. And for this, basically, you have to reconstruct in the equation for the perturbation who plays the role of the Newtonian potential. And what plays the role is this, which is related to perturbation in the density. Okay, very good. Now you say, I know what is the gravitational potential. I put it back in the equation with phonons, which are real, and then I have a vacuum with this anomalous density and mass have also a vacuum contribution, which is non-zero. Even in vacuum, these excitations are there, because in a certain sense, even when you have a condensation, not all the atoms are in the condensate. There are always excited atoms, okay? There is this so-called depletion factor. And then what you see is that this equation can be cast exactly in the form of a Poisson equation with emergent constant. Also, the cosmological constant is emergent. And you can ask yourself, is small or large with respect to the emergent gravitational constant? You define the energy of the lambda, the Planck, the annual Planck energy, where the only constant that is still there is H bar, so you are preserving quantum mechanics here. And what you get is that the ratio is rho a cube. This rho a cube must be much smaller than 1 in order for the condensate to exist, because you want to work with very dilute condensate. So the cosmological constant in this setting would be oddly tiny with respect to the Planck scale. So the cosmological constant, you see, has nothing to do with the vacuum energy of the phonon cut off at the Alien length scale, which would be the natural scale at which you have the new physics, the substratum. It has nothing to do with that. You need to rederive the geometrodynamical equation. In emergent gravity, you have to rederive the geometrodynamical equation to know what gravitates. Otherwise, you are fooled, and simply doesn't gravitate, the vacuum energy of the phone. And this energy scale can be several orders smaller. Quantum field theory, effective field theory reasoning fails to set up the scale of lambda, because lambda and G Newton are emergent scale. So you cannot really trust effective field theory argument in the emergent system to set the scales. This is another lesson. No? Can we go beyond? And rapidly, you can do the same procedure in a relativistic BC. These are not done yet in the lab. But you can, in principle, there is the well-known theory for relativistic Bose-Einstein condense, where you have relativistic atoms. This is interesting because what you have is a system where you have a much more complicated dispersion relation for your excitation, and you have two kinds of excitation, a massless one and a massive one. The massive one can be excited only at very high energy, so normally is irrelevant. In the non-relativistic clinic, it's the massless one that survives and becomes the standard phonons of the BC we do in the lab. And what is happening is that at low energy, you have the massless excitation, basically with local Lorentz invariance on a curved metric, where the metric is a disformal geometry, zeta mu flat spacetime, and the disformal term is done with the four velocity of the relativistic background flow. You have a transition where your spacetime looks like it's energy dependent. So you have a metric on the cotangent boundary. It's a metric which is a function of x and p. And this is something that people, for example, in doubly special relativity, for those of you that have heard about it, are now working on. And then you go at high energy, there is no gravity, you have flat spacetime, and Lorentz invariant, but with a different speed, a limit speed, the speed of light, not the speed of sound. So it tells you that, in principle, you can have a regime of transition of Lorentz breaking, even if the fundamental physics is relativistic, because you interpolate between two Lorentz groups with different limited speed. Anyway, so let's move on. And basically what we did was to pick up, you do the usual expansion around the background, but we pick up the background to be purely real. Why? Because if the background is real, you can show that the disformal geometry I showed you before becomes a conformal geometry. So in that case, the speed of sound becomes the speed of light. So you don't have Lorentz breaking. You are in a corner in which you don't have Lorentz breaking. Now what you do the equation for the excitation, you do the equation for the background, and they take again the form of the Nostrum gravity, where now you have a positive cosmological constant. In the non-relativistic case, the cosmological constant was negative, by the way. We're getting an anti-de Sitter, not de Sitter. In the relativistic case, you're getting a positive cosmological constant with an emergent G Newton. And this constant will be only corrected by the depletion factor that was relevant in the non-relativistic. Good. Now I close. This is I close with a paradox. Let's go back to where we started. Okay, so what we've seen. We have played basically at the level of toy models in convex matter physics. even if we were playing with toy models, we got much farther forward than a priori you would have guessed, because no-strong gravity is not GR, but it's not so far away from GR. It was the proto-GR. It was 2 years before GR, okay? And has many things in common with GR. Now you say, okay, but now let me do this exercise. Let's take the perfect fluid, the acoustic perfect fluid of my first example. That is a place where there is no UV Lorentz breaking, because I haven't inserted it. It's an idealized system. In reality, you take a Schrödinger equation, you do a Madelung representation, psi equals square root of rho e to the I theta, and you get perfect fluid without any notion of Lorentz breaking, because that was coming in BC from the interaction of the atoms. Okay, so I have a system like that. Nothing, I have an acoustic geometry. Is locally flat? Yes, it's a pseudo-Riemannian geometry. Okay, can I quantize the phonon? Yes, why not? You can. Okay, so then I can do this game. Take a point in this geometry, and I quantize, basically, I do exactly the Jacobson construction. I send a bunch of phonons through this the horizon. I perturb the Rindler wedge. And what is going to be the variation in the entropy? I have only a geometry, I have phonons. The vacuum is the Minkowski vacuum. I define the entanglement entropy is going to be proportional to the area. I do the Reichenau equation, can be applied even in this setting. It doesn't know anything about the equation of motion. So let me do it. I do it the same way, and then I get the Einstein field equation. So I started with acoustic geometry, and the geometrodynamics is Einstein field equation. Hurrah! But I cheated, evidently. We know that the field equation are the hydrodynamical one. So where I cheated? I'll give you 1 minute. Then I so 10 minutes. But don't feel, I mean, basically, not even Ted told me immediately the answer. So it looks like we have cheated. Now, clearly there must be something wrong with this reasoning. Now, how we can derive the Einstein field equation starting from an unknown system? The cheating where it is that in the derivation, when I open the Q, what I do? I write that the perturbation of the horizon is done by a killing current, which is the contraction of a covariantly conserved stress energy tensor with the killing vector that generates the horizon. But you have seen the equation before. I get an Ostrom, and what gravitates? The stress energy tensor, no? The trace of the stress energy tensor gravitates. So the problem what it is, that there is an hidden assumption in Jacobson derivation. And the hidden assumption is basically the covariant conservation, the fact that what gravitates is the stress energy tensor, which is covariantly conserved. And for those of you, what it means that you are, with this assumption at the root, what it is background independence. So when you do the spacetime thermodynamical at Jacobson, you are really putting in that you are assuming that your theory is background independent, it's different variable. If I do this step in analog gravity, I do an ungranted step because that is not what gravitates, and that is what is the difference. No? Now, can we go on somehow? Good question. The problem to go on has to do with the fact that somehow you should find this kind of mechanism. Of course, it's not going to be a death matter system like the one we do in the lab, right? We have just learned lessons. Is a mind teaser. These kind of toy models at least are clearing up the kind of mechanism that may be at work and the misconception we have, like, see, for the cosmological constant. It shows you that once you adopt the emergent gravity system, the emergent gravity framework mindset, this looks like prep talk, you know, the mindset for in a company. Okay, you must have the right mindset. The right mindset, you see that the cosmological constant goes a problem evaporates, or in a sense, it's not a problem you can deal with at the level of the emergent reactive theory. The information loss problem is the same. You cannot there are things you can ask and things you cannot ask in the emergent system. Now, what we can do is evidently true that if you want, on the other side, it looks like this condensation mechanism smells that somehow gets so close in system which should not have anything to do with gravity, so close to the equation of gravity that maybe it's worth understanding if you can do something more. It's clear that you have to set the Gross-Pitayevsky equation, take it out of the box, because the Gross-Pitayevsky equation, for example, is in a Newtonian box. The relativistic equivalent of the Gross-Pitayevsky is in a Minkowski box. You have to take away the box. There should be no space-time which is contained. There must be a space which is not space-time in which it is contained. So that is, for example, what Daniele is trying to do. There may be other ways, and maybe it's not this kind of Gross-Pitayevsky, the right equation. I'm just saying that the mechanism of compensation seems to me that has still something to say before we abandon the idea. And regarding the other point I want to raise is that we also have to think that you cannot just play with the model. You have always to confront with observation. I mean, there is the possibility. You have seen we have already constrained. Some scenarios are heavily constrained. So that is a guidance we have. It's exactly because there must be, if you want to do emergence, evade the Marov and Weinberg-Witten theorem, there must be this mesoscopic regime. This symmetry must be emergent. So they open the door for phenomenology. That is a crucial tool that we have in our hands. We should use it. We should use it. So whenever you do a model, you have to think at the mesoscopic physics is induced. Even if maybe you don't have the precise number of the scales which will induce, at least with kind of new physics will induce in the mesoscopic regime. So the mesoscopic regime should be in each model of emergent gravity a part of the research where we should pinpoint how to really inquire nature and see if there is this behavior. And there are a lot of possibilities. If you need high energy, there is high energy astrophysics. If you need high precision, there are tabletop experiments. The tools are there nowadays, and they are improving by the day. So it's very important to keep this in mind. So, okay, this was just a summary of the lessons that we got in this brief journey. And I don't want to say anything more. I just want to say thank you.